ME347, Example 17. A combustor heats air inside a tube with a constant area of 0.0185 square meters by burning fuel. The inlet flow has a temperature of 604 Kelvin, a pressure of 557 kilopascals, and a Mach number of 0.40. At the burner exit, the temperature is 900 Kelvin. For part A, sketch the temperature entropy diagram for this flow. Next, find the rate of heat transfer to the air in the combustor for two cases. For part B, for the conditions given above, and for part C, for the maximum possible. For this problem, we will assume steady, uniform flow of an ideal gas with constant specific heats. We will also assume that the combustion products can be modeled as air. Finally, we will assume constant area for the tube with negligible friction. For part A, sketch the temperature entropy diagram. Before doing so, let's look at a schematic diagram for the flow. Air enters the frictionless tube of constant area A on the left, then flows to the right from section 1 at a specified temperature, pressure, and Mach number to section 2 at a specified temperature. While the air moves from section 1 to 2, heat has been added to increase the temperature by 296 Kelvin. Thus, for the temperature entropy diagram, the flow begins at section 1 and the specified conditions are sufficient to fully define the state. Next, since the Mach number is less than 1, the flow is subsonic. Thus, the process moves to the right along the subsonic part of the Rayleigh line for heat transfer in a frictionless duct. For part B, where we are calculating the heat transfer for the specified temperature at section 2, the exact location along the Rayleigh line is not yet fixed. However, we will assume for now that it lies somewhere before the choked flow condition at maximum entropy. For part C, for the maximum heat transfer possible, we will then solve for the conditions at state A and verify that our assumptions about the properties at section 2 for part B are valid. For part B, calculate the rate of heat transfer from section 1 to section 2 for the specified conditions. To begin, we apply conservation of energy for steady flow to a control volume containing the airflow from section 1 to section 2 to get an equation to solve for the heat transfer per unit mass, which is equal to the change in enthalpy and kinetic energy. Note that this equation can be used in its original form in terms of the local properties, or we can substitute in the definition of stagnation temperature. For this example, we will show that both versions will of course give the same result. Next, in order to calculate the total rate of heat transfer, we need to multiply the heat transfer per unit mass by the mass flow rate. By conservation of mass for steady flow, the mass flow rate can be calculated at section 1, 2, or A. We will perform this calculation at section 1. We begin by calculating the speed of sound for an ideal gas with constant specific heats to be 492 meters per second at section 1. For our Mach number of 0.4 at section 1, this corresponds to a local velocity of 197 meters per second. Next, using the ideal gas law, we calculate a local density of 3.217 kilograms per cubic meter. Finally, we multiply these values and the cross-sectional area to get a mass flow rate of 11.7 kilograms per second. Again, since the flow is steady, this mass flow rate is the same at every location in the tube. Looking back at the previous slide, we now need to get the properties used to calculate the heat transfer per unit mass. First, we already know the temperature at both section 1 and section 2, so the enthalpy term can already be evaluated. Second, we just evaluated the velocity at section 1, but we still need to evaluate the velocity at section 2 to evaluate the kinetic energy term. Referring back to the temperature entropy diagram, we note that the process from section 1 to section 2 lies along the Rayleigh line. Thus, we need to use the Rayleigh relations for these calculations. Since we know the Mach number at section 1, we use the local to critical temperature relation to calculate a ratio of 0.6151. Then, from the temperature of 604 Kelvin at section 1, we calculate the critical reference temperature at state A to be 982 Kelvin. Next, we can use the known temperature at section 2 of 900 Kelvin to calculate a ratio of 0.9165 for section 2. Finally, we want to use this value with the relationship at the top to calculate the Mach number at section 2. But once again, there is no closed form solution, so we must use either a figure or an online calculator. We will use a figure for Rayleigh flow for an ideal gas with specific Keats ratio of 1.4. Begin by noting from the legend, the static to critical temperature ratio is indicated by a dashed blue line and is plotted using the y-axis on the left. Also, note that we could have used this figure instead of doing the first calculation from the previous slide. In particular, for the Mach number at section 1 of 0.4, we read upwards to the dashed blue line and then horizontally to the y-axis on the left to get a temperature ratio of 0.62, which is the same as before. For the new part, we use our calculated value for the temperature ratio at section 2 of 0.9165 to read horizontally back to the dashed blue line and then downwards to get a Mach number of 0.600 at section 2. Note that when using these figures to read property ratios, you should be able to get at least two significant figures. Because I typically also use MATLAB for these example problem calculations, I list the results with 4 significant figures for intermediate calculations. Now that we have the downstream Mach number, we calculate the speed of sound at section 2 to be 601 meters per second, which corresponds to a local velocity of 361 meters per second at a Mach number of 0.600. Note that even though the area of the pipe is constant, the flow is speeding up while the heat is added due to the expansion of the gas. Also, note that our assumption that section 2 is somewhere on the Rayleigh line before the critical state is correct. Substituting in the values needed to calculate the change of enthalpy and kinetic energy into our conservation of energy equation, we get that the heat transfer per unit mass is 34.3 megajoules per kilogram. Finally, multiplying by the mass flow rate calculated earlier, we get that the rate of heat transfer is 4.02 megawatts. This magnitude corresponds to an inlet flow for a large gas turbine being used to produce electrical power. Before moving on to part C, we repeat this calculation using the stagnation properties. Again, referring back to the temperature entropy diagram, we see that we need to calculate these values using the isentropic stagnation relations. At section 1, the stagnation temperature is 623 Kelvin, and at section 2, the stagnation temperature is 965 Kelvin. Calculating the rate of heat transfer, we get the same value of 4.02 megawatts as before, as expected. For part C, calculate the maximum rate of heat transfer. This corresponds to choked flow with section 2 at the critical state A. Because we needed to calculate this reference state temperature for part B, we already know that it is 982 Kelvin. Using this value, we get that the velocity at the critical state A is 628 meters per second. Because the temperature and velocity are both much higher at the critical state A, we now get a much higher rate of heat transfer of 6.53 megawatts. Finally, note that adding any more thermal energy to the flow at this point is impossible because the flow is now choked at the critical state, corresponding to a Mach number of 1. Also, the entropy is at its maximum possible value.